This video I'm going to tell you about linear equations, and in that we'll talk about linear equations in one variable, talk about linear equations in two variables, and in particular things about slopes and lines, say parallel, perpendicular lines, horizontal lines, and vertical lines, all that good stuff. And then the last thing I'll tell you about in this video is about rational equations in one variable. Technically not a linear equation, but it's all thrown together in this little section. Okay. So a linear equation in one variable has this form ax plus b equals 0, where a and b are the real numbers and x is the variable. And typically you're asked to solve an equation like this. So let's do a couple examples. You want to solve 3 times x plus 2 plus 5x minus 2 equals 1. And it doesn't quite have this form equals 0 like it does up here, but it could be rearranged to do so, right? And the idea is you could combine a bunch of like terms to figure out what a is. You can combine a bunch of like terms to figure out what b is and get 0 on a side. Anyway, when you want to solve an equation though, right, you just want to get x by itself here. So we want to try to just do what we can to get x by itself. And so if we're going to do that, you're probably going to distribute this 3, and you get 3x plus 6. And then plus 5x. And the other thing I did here is I went ahead and I added this 2 to both sides. So that's how you get a 3 over there on the right side. So then what else am I going to do? I'm going to combine my x's to get 8 x's. And the other thing I did is I'm going to subtract the 6 over here, and I get negative 3 when I do that. And the last thing you do is you divide by 8, and your answer would be negative 3/8 is x. So you just get a single number as an answer for right now. Let's solve another one that's harder because it's got some fractions in it. So 1/5 y minus 2/3 times the quantity, 4 minus y, is 2/15. And in this, I think it's a good idea to just try to get rid of fractions. And when you've got an equation, you can do that. You can clear fractions. You can get rid of them. Because I know one of my equation solving principles is anything I do to one side, it's okay as long as I do it to the other side. And so a convenient way to get rid of 5, 3, and 15 simultaneously would be to multiply by their least common denominator. In other words, what do they all go into? And they'll go into 15. So that's why you notice I've multiplied I'm thinking of these as 3 different pieces. I multiplied all 3 pieces by a 15. And the point is, now this 15 and the 5 will cancel and give me a 3. This 15 and this 3 will will cancel and give me a 5 over there on the right. And then finally the 15s over on this side cancel altogether. So what you're left with to track through that again is this just reduces to 3y because the 15 and the 5, 15 divided by 5 is 3. What did I do? I canceled the 15 and the 3 to get a 5, and I wrote it over there on the right side. You could have put it over here next to the 2 if you're comfortable with that. I'm going to do that in the next step, actually. And like we said, over here, the 15s just go away. All right, so then, don't be alarmed here. I know I can multiply in whatever order I want, so I'm just going to think of that as negative 10 in the next step. So that's where that negative 10 comes from. But then now this looks pretty similar to the previous equation that we just finished, where you're going to distribute the negative 10 through, and you get negative 40, and then plus 10y. And so 3y is still left alone, and 2 is left alone. But now you're going to get the y's together, so it looks like there's 13 of them. And then the other thing you'd probably do is you'd probably add 40 over to the other side. And so at this point, it looks like 13y, it's 13, is equal to 42. And so y is 42/13. And that's your final answer there. So we've practiced solving a few linear equations in one variable. Let's move on to linear equations in two variables. And they have the form ax plus by equals c. And here, x and y are the two variables, and a, b, and c are just some real numbers. So you'll see actual numbers there typically for a, b, and c. And so lo and behold, the graph of this equation is a line. Now this is sometimes called the standard form of a line. It's not the best one to tell me information about the line itself. And there are better ways to write the above equation that will actually give us more information about the line. So for the rest of this video that we're talking about lines, we're going to look at 2 more convenient equations of a line that again yield some more information. You might be thinking, what kind of information about a line should be important to me? And really the key feature about a line is the measure of its steepness and direction, which is called its slope. And we want to talk about what slope is, and then we'll look at how slope helps me determine the equation of a line. So if I've got a line, and remember it's just connecting through 2 points, and I've named the points x1, y1 and x2, y2, then to figure out what the slope is, what we want to do is we just want to figure out, how far to the right do we go to get from the first yellow point to the second yellow point, and how far, bottom to top do we go is one way to think about that. So maybe a less confusing way to say that, I'm going to look at the rise, which would be y2 minus y1, and I'm going to look at the run, which would be x2 minus x1, and what the slope is it's the rise over the run. And so in numbers, that would be y2 minus y1 divided by x2 minus x1. So that's your formula that you want to use when you actually have some coordinates for these points. So let's do a little example, and I picked a gross one to try to work through like a complex fraction with you to remind you how that goes. So we're going to find the slope of the line through -2, 3, and the other point is 1/4, 1/2. So we're just going to implement this formula, rise over run here. I'm going to subtract the y coordinates. It really doesn't matter which one you start with as long as you're consistent in the top and the bottom. But just to be consistent with the formula I wrote down, I put 1/2 first and then -3 here. So I'm subtracting the y coordinates. And then that's divided by, since I started with 1/2 on the top, I'm just saying you have to start with 1/4 on the bottom then, right? That point's x coordinate. As long as you're consistent, you're golden. Anyway though, I've got 1/4 minus -2. So that's where that extra negative's coming from if you're worried. But then now here, this is something where it's probably convenient to get this as a single fraction and to get this as a single fraction. And so if I do that, I'm going to get common denominators in the top and the bottom. I chose to do it separately here. If you're comfortable clearing fractions all at once, if you know how to do that, fantastic. Anyway though, when you get a common denominator in the top, that reduces to -5/2, and the bottom is 9/4. And the whole point is now you can think about it's this fraction divided by this fraction, and we know that we get to change this division sign to multiplication by the reciprocal of 9/4. And I think that is the next step. And what does that look like? 1 second. There. Equals -5/2 times the reciprocal of the bottom. So again, times the reciprocal of the bottom. And when you do that, I think you see the 4 and the 2 can simplify so that you have a 2 left here, and that's where I'm getting a 10 from. So it'd be -5 times 2 over 9. Anyway, the slope of the line through these 2 points is -10/9. And again, that's a measure of its steepness. And what it also can help me do is it can help me figure out some other points that are on the line. So to try to demonstrate that, and again, this rise over run idea, here's this point, -2, 3 that we knew we were at. What I'm saying is, how could I get to other points on the line? How you could interpret this? You can interpret the negative as, say, going up 10, but the negative is telling me to go left 9, right? So left is like the negative direction. So if I go up 10 units, that takes me up to 13. And if I go left 9 units, that takes me over to this point right over here, which looks like -11, 13. And then similarly, another way I could think about that, if I get rid of this stuff here, another way I could think about what this -10/9 is telling me is I could think of that as going down 10. So down is the negative direction, and then right 9. So like I already took care of the negative with down 10. Now I'm just going to go right 9. And if I do that, I go down 10 units, and then I go right 9. It takes me over to this point right here, which looks like the point 7, -7. So anyway, that's how you could use that rise over run idea to get from one point to another nice point on the line. Okie dokie. And so let me get rid of some of this stuff, and we'll move on to the next piece. And it's almost there. Okay, so what are the two useful equations of a line? So remember I said that this, if I scroll up a little bit, here's what like the standard form of a line is, but it's not useful. Like nowhere in there can I see very clearly what the slope is, say. And the slope is important, right? It tells me like what are some other points on the line and how steep is the line. So this is not super useful for that. So what are some other ways I could write the equation of a line that's not that? So the first useful equation we'll talk about is point slope. The point slope equation is this. It's y minus y1 is equal to m times x minus x1. And I've drawn you a little picture over there. And what I'm trying to suggest on my picture is that you know one point that's on the line. And the other thing that I assume that you know if you're going to use this equation is the slope of the line. So you have to know two things to use point slope, kind of like it says. You have to know a point on the line, and you have to know the slope of the line. From there, though, you can build the equation of the line from scratch. So let's practice. Let's find the point slope equation of the line through those 2 points we just got done playing with in the previous example. And I picked those 2 points because, well, if one of the things I have to know is the slope of the line, we already did that. We got it was -10/9 in the previous example. So now what do you do next? Now you pick the most convenient of the 2 given points, And you just substitute those in for y1 and x1 into the point slope formula. So of these two that I have circled here, or really boxed here in purple, the yellow one's probably the more convenient one. I don't want to play with a fourth and a half. So we're going to substitute -2 in for x1 and 3 in for y1 right here and right here. And of course, I'm going to put my -10/9 here for the m. When I do that, it just looks like this. So notice you leave the y all by itself. You leave it alone, right? You don't plug anything in for it. And you leave the x that's in white. You leave the white x alone by itself. I mean, you don't do anything to it. And really the last thing, if you're asked to put your equation in point slope form, what you might do is just like resolve any goofy like double negative signs. So your final answer would just be the y minus 3 is -10/9 times x plus 2. And that's a perfectly good answer in point slope form of the line. Now, the second useful equation of a line is maybe the more popular one, and it's called the slope-intercept form. And to draw you a little picture here, you see this equation as y equals mx plus b, and maybe what is this b here, because we all know what m is now. This b is the y-coordinate of the y-intercept. Remember, the y-intercept goes through the y-axis, so I know its x-coordinate is 0, so the y-coordinate b here is what we'll call, is the useful thing from the y-intercept. So what does this assume that you know if you're going to use y equals mx plus b? If you can write your line down, that assumes you know that you know the slope m, and you know the y-intercept, you know its y-coordinate b. So let's see, how would you do that? So let's try to find the slope-intercept equation of the line through those 2 points that we've been playing with so far. And again, I picked this one because we've done a lot of the work already. We've already found what the slope is. It's -10/9. And now we want to get our final answer in the form y equals mx plus b. And for this, there's 2 ways to do it. Option 1, again, pick the most convenient of the 2 given points and just substitute it into the point slope equation that we just got done playing with. And we did that earlier, so I'm going to pick the point -2, 3. Remember, that was the convenient one instead of the 1/4, 1/2. I substitute those in. But now the game is, let's try to get y by itself. And so that's the new thing. So you sub into point slope and then solve for y. And once you simplify everything after you solve for y, you'll be in y equals mx plus b form. So if I'm doing that, what have I done here? I'm going to take the -10/9, I'm going to distribute it through. That's where I got the, let's see, this would be plus, but you're still going to distribute this minus through. That's why it stays minus. So you notice -29. Hope you tracked that okay. And now what are we going to do? Well, we want to get y by itself, so let's add this 3 over to that side. And if I do that, it looks like that. And then 3 is the same thing as 27/9. And so when you do -29 plus 27/9, you get +7/9. And I circled that, highlighted that in blue because I was using blue for what b is earlier. But again, just to demonstrate, we started in point slope form, and when I solve for y and I simplify everything on this side, it turns into y equals mx plus b form. Where, again, this is nice because you can read off what the slope is. Oh, I see the steepness is 10/9, and the minus says that the line's going downward. And I see that it goes through the y-axis at the 7/9 tick mark. So that's kind of a nice thing to be able to do, to read something on paper and then also be able to think about what it looks like. Now, that's option 1, all right? So you kind of use point slope along the way. Now, option 2 is what I've grown a little more fond of over the years. I've been doing this a while. Option 2 is to pick the most convenient of the 2 points again, but let's just sub it directly in to slope-intercept to find b. So here's slope-intercept, y equals mx plus b, and I've highlighted in yellow. I'm actually going to plug my convenient coordinates, which were -2 and 3, you know, that point we've been using. I'm going to plug those in for x and y now. So what's that look like? So -2 is x, 3 is y, and then I put -10/9 is m plus b. But what I hope that you notice is that everything is filled, all but b is a number now. And so you could solve for b, and that's exciting. And so I get 3 is equal to 29 plus b. And at this point, remember, just subtract 29 to the other side. Since you're adding it to b, you want to move it over by subtracting. And so 3 minus 29. Now this is 27/9 minus 29 is 7/9 again. And so I get that same 7/9 this way. So you can pick whichever one you're more comfortable with, option 1 and option 2. I encourage you to practice both because that's going to make you a little bit better at all this algebra, but you can kind of pick to one and do it more often if you're into it. Let's talk briefly about parallel and perpendicular lines. 2 lines are parallel, they have the same slope, and so remember, parallel means they don't intersect. And just to give you a quick example, y equals 3x plus 5 and y equals 3x minus 27, those are parallel because, as I've highlighted in this greenish color, they both have a slope 3. Same slope, that means they're parallel. Two lines are perpendicular, and remember, perpendicular means they intersect, but it's at a right angle, a 90-degree angle. So they're perpendicular if their slopes are opposite reciprocals. Opposite here means that they have different signs, so one's plus and one's minus. And reciprocals, remember, that means that you flip it. So if it's a fraction, you just flip it, or if it's a whole number, you put it under 1, right? That's taking its reciprocal. So let's just look at a quick example here. Y equals 5/7 x plus 2, and the line y equals negative 7/5 x plus 2 plus 51. Those are perpendicular to each other because I notice that these fractions are, one's positive and one's negative. That's opposite. And I notice that I flipped it. 5/7 became 7/5. So I've got opposite reciprocals. So that's how I know they're perpendicular. In other words, I know just by looking at these equations that they intersect at a right angle. So that's kind of nice. All right, horizontal and vertical lines. And let's see, a horizontal line through a point A comma B, it has the form just y equals b. And maybe what you might notice here, the slope is equal to 0, right? It's like 0x plus b is the same thing as this here because there is no x. That means it must be 0x there. So a horizontal line has slope 0. And just to give you an example, if you've got a picture, let's see here. So here's this picture, and there's that line. It looks like it goes through the point negative 2 comma 2. We could write its equation down. And if you're tracking how I'm coloring things, the equation should just be y equals the y coordinate of that point. So y equals 2. All right, so vertical lines work a similar way. So a vertical line through the point A comma B has the form x equals a. So vertical lines are a little bit goofy because up until now, everybody's been y equals something. Vertical lines are x equals a number here. Also, I don't remember if I wrote this down earlier, so I should write it down now. A vertical line has an undefined slope. So undefined slope. You might have heard the term no slope before. Really, no slope would be 0 slope. So no slope would probably be better describing a horizontal line. Vertical slope, you should be consistently just think of it as an undefined slope. Okay, and so I'll get rid of that, and then I got a little example just to show you how this works here. So here's my line, and it looks like it goes through the point 2 comma 1, and I want to know what its equation is. And again, if you're following along with how I'm coloring things, it's vertical, so I know it's x equals something, and what it equals is just what's the x coordinate of the point that you know. So x equals 2 is the equation of this vertical line. But the last thing in this video, let's talk about rational equations. Remember, rational expressions, we're allowing like x's to be in the denominator. So like fractions of polynomials technically. And now we're saying we can solve equations that have fractions of polynomials in them. And what is like our golden rule in math? It is that you cannot divide by 0. And another way to think about that is to say that the denominator can never be 0. So if I'm asked to solve this rational equation, so here I've got these rational expressions here, and technically a whole number is a rational expression too. Anyway, remember it's equation because it's got an equal sign. I want to solve this. So at the end of the day, I want to do some magic algebra stuff, and I want to get x equals some number here. All right, so how on earth do we do that? What I'm saying first is, you should take a look here. I'm nervous because I've got a denominator, and it's not a constant right now. It's not fixed right now. It's got a variable in it. So like, is there a value of the variable that would ever make the denominator 0? And I see that, ooh, x can't be 3, because if x is 3, then this is 0 down here, and this is 0 down here. And then I divide by 0, and like, I don't know, the world ends or something. And so what we're going to do is we're going to call that bad x value, we're going to call it a restricted value. So in this case, let's say 3 is a restricted value. So we've identified what the restricted value is. I cannot have x equals 3. Not allowed. So how do you actually go forward, and how do you solve these things? So the first thing you ought to do is find the least common denominator for all the fractions that you see in the problem, or all the fractions on both sides of the equation, to be more technical about it. The second thing you should do is you should use that LCD. You're going to multiply both sides of the equations, and what the point of that is, it's to clear fractions. When the dust settles, you shouldn't have any more fractions. And that's great. You should have a nice like linear equation, or depending on if you've seen quadratic equations yet, you might have a quadratic equation. So you try to solve the remaining equation. And then the last thing that you do, assuming you've done step 3 and you get x equals a number, you need to check, is the number you get one of the restricted values? Because you're only allowed to keep answers in step 3. You're only allowed to keep the answers that are not restricted values. So let's go through and try to solve this equation that we've got here. So step 1 is to try to figure out what the LCD is, In this case, the only denominator is x minus 3, so that is the least common denominator. And what we're used to doing is trying to like put fractions together and give them a least common denominator, to write things as a single fraction. But if you're interested in solving an equation, that's not what you're going to do with it. You're going to take the LCD, just like it says in step 2, and I'm going to multiply everything that I see on both sides by the LCD. And what do I mean by everything that I see? How I'm looking at this is I've got 3 terms here in this equation. I'm going to multiply each one of them by x minus 3. And so if I do that, that looks like this. So again, I've taken each of the 3 terms and I've multiplied it by an x minus 3. And again, that's consistent because I've done the same thing to both sides, and I've done the same thing to, to everything on both sides. Now, what's the point of this? So I say to multiply both sides, but then I tell you why. I tell you why is to clear fractions. So the point of this step here is to try to see if you can get rid of any of the fractions that you have. And what I've done is, I noticed that here's an x minus 3 in the top and here's an x minus 3 in the bottom. And I also see that here's an x minus 3 in the top and here's an x minus 3 in the bottom. I can cancel those. And that's what I've done in the next step. So that's how you want to use the LCD for these kinds of problems, to get rid of any fractions that you see. And now if you look at what are you left with, well, I'm just left with an x plus 4 here. 1 times x minus 3 is just that x minus 3, and I'm just left with the 7 here. So all I get then is the x plus 4 plus the x minus 3 that's left, and then equals 7. And this is step 3, where we're going to solve whatever the remaining equation is that I get. And in this case, this is a nice linear equation that we end up with. So again, that trick of multiplying by the LCD, it transforms this yucky rational equation with fractions in it. It transforms it into a nice linear equation. And so if we go through and solve this, it looks like there's 2 x's there, and then plus 1 is 7. Move that 1 over, so you get a 6 over on that side, and divide by 2, so you get 3. We're pretty pumped. We solve the remaining equation. We get x equals 3, but now we're on to step 4. We only keep answers that are not restricted values. So let's take a look. And up here we said, okay, the restricted value is 3, so x cannot be 3. But then I look at my answer for part 3. Wait a minute, that's the restricted value. So I can't keep it. That means that there's no solution, right? We didn't find any other numbers that would work. It looked like x equals 3 was the only number that might work, but I know that it can't work because it makes me divide by 0. So therefore, in this case, there's no solution.